up, grade 11s? It is Maths Monday. I am Looney, and with me today is Dina. Dina, how are you doing?
Hello everybody, hello Looney.
Hello.
Doing very, very well and ready for another jam-packed session.
Great, so what are we doing for the grade 11s today?
Grade 11s, we're going to be working with lots of concepts in trigonometry. We're going to have 3 sessions today. The first session we'll look at the key concepts around identities. We'll look at reduction formulae and simplifying ratios that have got numerical angles as well.
All right, grade 11s, you heard all of that. Dina, I'll send you to your board.
See you now.
Guys, let me just tell you a few bits of information that you need to know in order to keep in contact with us during the whole show. So on Facebook, you can keep in touch with us on facebook.com/learnextra. Ask me any questions you may have, everything you want to know about the show, and if you have any questions for Dina, I'll ask you during the break and we'll keep interacting throughout that on Facebook. On Twitter, you can catch us at Learn Extra, and on our page where you can download the notes, the videos and the schedules, it is learnextra.co.za/live. I'd like to thank Macmillan for sponsoring our show, and with all that said, I'd like to hand over to Dina.
Thank you, Looney, and yes, thank you Macmillan, because I am using quite a lot of the examples from their book, Clever, Keeping Math Simple. So you'll be able to, if you have that book already, be able to follow with us. Otherwise, just use the notes that we've posted up. Well, it is trigonometry, it is reduction formulae and identities. So let's get straight through it. Let's go through some of the key concepts, some of the things that you've learned from grade 10, and then maybe some things that may be new. I'm not going to develop any of the theory. I'm going to do quite a number of examples to just show how the theory actually works. And yeah, if you've got any questions on the theory, do post those on the page. So what we'll be doing in the lesson is to define the trig ratios on a system of axes. We're also going to establish the signs of the trig ratios in every quadrant. We're going to reduce ratios of angles in the interval 90 to 360 to ratios of acute angles. And then we're also going to reduce ratios of negative angles and angles that are larger than 360. So those are the 2 key concepts we're going to look at. And then we're going to look at a little bit on proving identities. From grade 10, you would have already established what the coordinates are on a system of axes and what the definition is for sine theta, and that is that it's y over r. Cos theta is the abscissa over the radius, and tan theta is the y over x. So those 3 definitions we're going to use quite intensively throughout the session. Right, then the signs of the ratios in the 4 quadrants. We're going to establish that. There is a rule, and your teacher may have called it cast rule, and it has got a significance. And we've got the system of axes from 0 degrees through to 90, through to 180, 270, 360, remembering that in an anti-clockwise direction, the angle is positive. That's quadrant 1, quadrant 2, quadrant 3, quadrant 4. And what it's saying is that in the second quadrant, the sine ratio is positive and all the other ratios will be negative. So we're only capturing the positive one. So if we put sine on there, it means that cos and tan are negative. Then we have the third quadrant, which has got tan as positive, and then all the other ratios are negative. And in the fourth quadrant, we have cos is positive, so therefore all the other ratios are negative. So what we're saying, for example, is that sine of 120 will be positive. The tan of 240 will be positive. The cos of 300 will be positive. But the cos of 120 and the tan of 120 will be negative because it says all other ratios are negative. The sine of 240 and the cos of 240 will be negative because all other ratios are negative. And for example, cos 300 will be positive, so sine of 300 and tan of 300 would all be negative. So this diagram we're going to keep with us all the time. We're going to refer back to it, keep it with you whenever you're doing any work on reducing angles to an acute angle. We are going to work with that formula. And then your identities are the 3 major ones, and those will be on your formula sheet, but it's good to memorize them. Firstly, the quotient one, where tan can be written as sine over cos, and the squared identity, that's sine squared plus cos squared, no matter what the angle is, will always equal 1. And from that identity, we can also get that 1 minus cos squared is sine squared, and we can get that 1 minus sine squared equals cos squared. So there's a couple of theory parts that you need to keep with you when we're doing anything, so you can refer back to. The identities, the quotient one for tan, and the squared one, and its subsequent or its ancillary sort of subsections of that equation gives us sine squared and what cos squared is all about. So those are really our basic identities. Then one thing that's not on this diagram is that in the second quadrant, we're always going to define any obtuse angle as 180 minus an acute angle. And in this quadrant, we're always going to define this angle as being 180 plus an acute angle. And in this quadrant, we're going to have 360 degrees minus an acute angle. So we now have, for any of those angles, for example, 240 I've chosen here, we can say that the same thing as 180 plus 60 will give us 240. And 300 would be 360 minus 60 would give us 300. So we would like to write all these ratios in terms of these pink formulae. They are going to be able to work out what that reduction will be. And when we get to that question, I'll show you exactly what we mean when we want to reduce. Right, then we have the reduction formulae for, as I explained just now, we've got this one, the 180 plus as quadrant 3, this one as quadrant 2, and this one as quadrant 4. So those are standard. We are always going to use them. They're not going to change. And then we've got some co-functions. So we've got 180 and 360. They lie on the x-axis. So if one works off the x-axis with angles such as 180 minus theta and 180 plus theta and 360 minus theta, or even negative, the ratio that we're going to reduce it to will remain unchanged. But when reducing angles of 90 plus or 90 minus, any of these angles, I should actually draw this in a different color. These functions here, the ratio changes to the co-function. So what this really means is that if I have the sine of 40 degrees, then that's the same thing as saying the cosine of 90 minus theta, which is a cosine of 50. So we talk about them being co-functions because all that happens is that I attach the co to the sine. But if I was looking at the cosine of 60, then because I've already got a co, I would drop the co and I would get that it's the same as the sine of 30 degrees. So these angles over here are complementary. What does that mean? That 60 plus 30 gives me 90. And so the reason they are called co-functions is because you either attach a co to the sine, or if you've got the co, you drop it. And so it's just a prefix of the word that affects the actual trig ratio. But when you add the two angles together, you actually get a sum of 90 degrees. Okay, so I think that talks about the reduction for me. Right, let's look at some examples. Simplify the following expressions. Okay, so the first thing we need to look at is, and I'm going to work with A first. So I'm just going to rewrite A over here. So we've got cos squared of 180 minus beta, and we're dividing that by sine of 90 minus beta. And then I'm multiplying it by tan of 180 plus beta. Remember just now I said to you that you cannot do reduction formulae if we don't have the diagram that helps us to resolve which quadrant we're actually in. So always draw the Cartesian plane 0, 90, 180, 360. I'm not going to fill this in, but fill in the quadrant where the angle will be. So 180 minus beta will be second, 180 plus beta will be third, and 360 minus beta will be fourth. Then, first thing we're going to look at is the cos of 180 minus beta. Now, I know that it says cos squared, but we're not going to deal with a square just now. We're just going to first deal with the ratio. So our starting point is the angle. Where is the angle 180 minus beta? We've rotated all the way with a terminal ray all the way to the second quadrant. So one thing we haven't put in is what ratios are happening. So all are positive, sine is positive, tan is positive, and cos is positive. So we've got what we call the cost rule. So in this second quadrant, we have that cos is negative because sine is positive. So we've got a negative cos beta, but now they said we need to square it. So brackets around that linear, and that's going to be squared, divided by. What is the sine of 90 minus beta? Remember with the theory, with the key concepts we looked at, that anything that adds up to 90, they are called cofunctions. So the ratio doesn't stay the same, but the ratio will change to its cofunction. I like to call that rule the COCO rule because the angles are complementary and the cofunction, you have to add that prefix to it. So I call it the COCO rule. Whereas with 180 minus, 180 plus, and 360 minus, the ratios remain unchanged. So sine of 90 minus, complement. So the complement is going to force me to create a cofunction. So I'm going to get the cofunction of beta. And then I'm multiplying it by. What do we look at first? The position of the angle. Which angle am I looking at? I'm looking at an angle that's rotated to a terminal ray in the third quadrant. The moment I'm in the third quadrant, the tan of that angle is going to be positive. So therefore, that reduces to the tan of beta. So when we talk about reduction formulae, we're talking about a formula that will allow us to rewrite that ratio as a ratio of an acute angle where the ratios are actually the same. So, for example, if I had tan 60 degrees, then if I add 180 to it, tan of 240 is also the same ratio. They're different sized angles, but that ratio is the same. And that's key to know, that we're working with the same ratio. So a reduction formulae, in essence, is just another way of writing a trig ratio, so that the ratios are the same size. And hence, we have these formulae that allow us to rewrite that complex angle as an acute angle. Once we've got that to that stage, then we can do some simplification, and we have that the cos can go into that cos, so we're left with a cos beta, and now we're multiplying it by tan. But a tan beta can be written as the quotient of sine over cos. Remember our quotient identity? It can be written as sine over cos, so we land up simplifying this as the same thing as sine beta. Okay, so reduction formulae is encouraging you to rewrite what appears to be a very complicated looking expression into something that can be rewritten as an acute angle. Now let's go up and see what we've got here. Right, now here's also something quite long, something quite complicated, and we're just going to rewrite it. Actually, we're not going to rewrite it, we're going to talk about it. Let's look at it in terms of this function. What about this new one? Now, when we looked at our quadrant over here, we saw that we had 180 minus, 180 plus, 360 minus. We did not have that. Cos x, cos 24, cos 90 minus x. I think we can do something like that, sine 66. We've got sine squared plus sine squared of 450 minus x. Okay, so that one does not look at all like any of the ones we've looked at. So there's a little bit of theory we need to discuss, and that is what happens with negative angles. Okay, and the theory about negative angles is that the sine of the additive inverse is the same as negative sine A, whereas the cos of negative a is the same as cos a, and the tan of negative a is the same as negative tan a. So if you change the angle to its additive inverse, you're changing the sign as well of the ratio. The only one that stays the same is the function that is symmetrical about the y-axis. And that function is the cos function. So cos, if you're drawing it there, you draw exactly the same thing on the side. It's a mirror image about the y-axis. And so you change the size of the angle, but the ratio stays the same. You change the angle, but the ratio stays the same. The ratio does not change. So this function, because it's symmetrical about the y-axis, change the sign of the angle, the ratio remains unchanged. Whereas with sine and tan, change the size of the angle, the additive inverse, that ratio will change. Okay, so that's what's very important about negative angles. So if we go back up, and we're trying to see, well, what is this tan of negative 180? And I can see that it's the same as the additive inverse of that angle. So we said that if you change the size of the angle, you change the sign of the ratio. So it becomes negative tan of 180 minus x, which is applying our negative angle rule. Cos x is already acute. I'm not going to do anything to it. Cos 24, we're not going to do anything to it. What about cos of 90 minus x? That becomes sine x. And sine of 66, I'm not going to do anything with it yet. What about sine squared of 450 minus x? Anything that's larger than 360 degrees, the terminal ray will be the same ray if you take away 360 degrees from that. So this one's going to be sine squared of 90 minus x. And now that we've got the cofunction, we can work with that cofunction. We can work with that reduction, and we can simplify that. And I think we'll take a break now.
All right. Mindsetters, don't forget to hit me up on Facebook at facebook.com/LearnExtra, and on Twitter we are at LearnExtra. We are going to take a very short break, so don't go anywhere. Welcome back, guys. I hope you guys are ready to continue with the question. Thank you so much for interacting with me on the page. I'll do as much as I can to ask any questions that you may have during the whole show. So right now, I'll take it back to Dina.
Thank you very much, Looney. Yes, we left off where we were trying to simplify a fraction that included reducing of a negative angle, and it included reducing of an angle larger than 360. So let's get back to where I left you. That was, we had already reduced, and we were sitting with these acute angles. Now, if we are to reduce to an acute angle, and they are already acute, then I'm not going to do anything with them until I've done some kind of simplifying around me to see what I'm left with. So I'm left with a tan of 180 minus x. So by the end of the session, you need to be able to spewing out which quadrant I'm in. I'm in second quadrant. Tan is negative in the second quadrant, so I'm going to get a negative of a negative tan x. And then I've got this cos x multiplied by. Now I've become clever. What's 24 and 66? That adds up to 90. So these two are cofunctions. So if I change that to sine 66 or to that to cos 24, I'm going to be able to divide. Now you'll find that these questions, when you are to reduce to an acute angle, say do not use a calculator. That's just because we need to see how you would use expressions to be able to simplify without actually going to find the values on the calculator. So I'm going to change that to sine 66 already. And then I'm going to get that all over sine x. And that's going to be sine 66. Then I need to add on a sine squared x. And I have a 90 degree. 90 is a complement, so I'm going to use the co rule, complement, cofunction. So that becomes the cofunction, which is cos squared x. Then, from there onwards, how else can we simplify this? Well, I have tan can be written as a quotient. Remember, it's either quotient or the square function, square identity that I'm looking for. That I can write as a quotient of sine x over cos x, and I've got times cos x over sine x. This I can already divide, and I can see that's 1. And then I've got on here these two terms. And what do these two terms add up to? The sum of the squares of sine and cos will always give us 1. So I've got a plus 1. Simplifying this gives us 1 as well. So 1 plus 1 actually gives me 2. So that very complicated looking fraction actually reduced down to a value of 2, which means that whatever x is, doesn't matter. That fraction will always come down to a 2. Okay. Right, so let's see a little bit more of reduction in action. Very popular question. If cos 25 degrees, and you can go to your calculator, you can find out what t is. But it's saying if it is t, express the following in terms of t. That is a traditional question for reducing. So because we're reducing, we're going to keep next to us all our little notes that we're going to have an angle in the second quadrant, we're going to have an angle in the third quadrant, we're going to have 360 minus, and we're going to have our quadrants. We're also going to, in the quadrants, have that everybody's positive, sine is positive, tan is positive, and cos is positive. So we're going to keep that information. We're also going to keep the information on the negative angles, that sine of negative A is sine A. We're going to have cos of negative A is cos A, and we're going to have the tan of negative A is negative tan A. So we're going to use some of that information, and we're also going to use the very popular Coco rule. So our Coco rule says that if I have a sine of 90 minus, then it's going to be the same as the cosine of A. So those two angles add up to 90. That doesn't look very well written. Let's just make this a little bit more legible. There we go. Right, so now we have cos 25 is t, express the following in terms of t. We can look at this in a very algebraic way, or we can look at it in a pictorial manner. I'm going to show you both ways, and then you can decide what you'd like to use. So if cos of 25 is equal to t, without a calculator, I could actually draw a triangle that has got a 25 degree in it. So how big is this angle here, if that's 25? Well, those are complementary. So that means this angle is 65. 65 and 25 is 90. And if cos of 25 is t, it means that my adjacent side, this side here, is t, and my hypotenuse is 1. So I could actually work out, that's my given information, I could actually work out this side over here, by using Pythagoras. So this side would be the square root of 1 minus, I don't know why my pen is not behaving itself today. Right, there we go. Square root of 1 minus t squared, just by using Pythagoras. So now I can define sine 25, tan 25, sine 65, tan 65. The moment I have an angle in a triangle, I can actually solve for the other three ratios. And I can solve for the three ratios of the angle that's complement to it. Okay, so a very powerful tool for you to be able to work with reduction formulae. So in this case, if I'm looking for the tan of 25, then tan of 25 would be opposite over adjacent, which would just be that. So my tan of 25 would be square root of 1 minus t squared over t. Okay. What about the sine of 25? Well, the sine of 25 is opposite over hypotenuse, so it would be that over 1. Now, I said to you I would show you an algebraic way of solving for this, and it would actually be something of this sort. We would want to ask ourselves, what is it that connects? What connects sine 25 and cos 25? How are these two connected to each other? The only way we can connect them is if we take their squares, then the sum of their squares will equal to 1. That's the only way I can connect them. So if they've told us that cos squared 25 is 1, then, or it's equal to t, then sine squared 25 is going to equal to 1 minus cos squared 25. And in that way, the cos of 25 is equal to the square root of 1 minus t squared. Now, if you remember from our diagram, cos, this should be sine, hey? This should be sine, so we've got the sine of 25. So if we go up here, on our diagram, we saw that sine of 25 was opposite over hypotenuse. So it's the square root of 1 minus t squared. So I've shown you a way of using the identity to find the unknown ratio. But for me, the most powerful tool is actually a diagram, because the diagram supports what you are thinking in the vacuum, which is really the identity stuff. Okay, so that would be the sine of 25. Sine of 65 I don't really have to go into. It's the same thing as cos 25 as a cofunction, or it's t over 1, whichever way you'd like to look at it. What I am interested in is, how do we reduce sine of 245? So what is the sine? And this is question D. What is the sine of 245? Okay, we did not put down our theory notes for nothing. Okay, we're going to use that. And the first place where we start is the position of the terminal ray. Where is the terminal ray? 245, which quadrant? Quadrant 3. So we're going to be able to reduce sine 245 as the sine of 180 plus how many degrees? We're going to have to add 55 degrees onto that in order to get to, or how many degrees must we add onto 180 to get to 245? And we certainly must make these calculations really simple, and either use your brain or use the calculator, but try not to write those formulae all the time, because in your matric final you're not going to have enough time to write down what the formula should be and then coming back. So we should already be saying that it's 180 plus, and I would always encourage that, right, we would use your calculator. But for those of you who have not yet done reduction formulae, I'm just going to write down what the formula would be. So terminal array is quadrant 3. This is in quadrant 3, which means that I'm going to say 180 plus 65 degrees. And the reduction comes in saying that this third quadrant angle is the same ratio, gives us exactly the same ratio as negative sine 65. And why is that? Quadrant 3 has got tan as positive, so therefore sine of that angle will be negative, and so we'll get it that it's the same as sine 65. So I can't say that sine 245 is equal to sine 65, and test this on your calculators. Punch in sine of 245, what does it give me? Sine of 65, what does it give me? Every single ratio in quadrant 1 will be a positive ratio. So if I put in a negative, it means I am taking the additive inverse of that ratio, which is what I'm saying that sine of 245 equals to. So that would be negative sine 65. And I can now go back to my picture and say, well, sine 65 I've already got. It's t over 1. So therefore, this must be negative t. Okay. And then we've got the tan of 205. Okay. We start at the same place. Which quadrant are we in? Tan of 205. Where is 205? Third quadrant. So third quadrant is 180 plus how many degrees? 25. So we get that this is the same as tan 25. Why? Why is that tan 25? Because if we go back in the third quadrant, tan is positive. So there is a tool for you to use to give you the angles. You don't have to guess. You don't have to memorize. If you go back and you use that tool, you'll always get the right value. So that's tan 25. And we've worked out before that tan 25 was opposite over adjacent, we've already worked out that that is the square root of 1 minus t squared over t. So we don't have to recalculate that. Okay, don't get into the habit of just restarting things from scratch. If they've been calculated, utilize them. Right, and then we have the sine of 385. Oh, this is an interesting one. Because do you agree, this does not, 385 is not an angle that is in the 4 quadrants as such. But if we rotate sine of 385, if we had to draw the sketch of this terminal ray, it would do something like this. It would start at 0 degrees, we would rotate all the way to 360, and then we'd have to rotate a little bit more. So the terminal ray starts becoming a second revolution. And so that's why with any angle larger than 360, okay, so if I have I would say to my calculator, put in 385, and I would take away my 360 degrees. So I land up in the quadrant that second revolution was going in. And so we see that that would be the sine of 25. The beauty of angles that are larger than 360 is that we don't need to worry about the sine. Because the terminal ray will land up in the same quadrant, the sine will then take care of itself, because we then go back to the original diagram of 180 minus 180 plus 360 minus. So we now have that this angle here, the blue angle, is 385, but this little angle here is my 25. So I'm saying that sine of 25 is exactly the same as sine of 385. And we've worked out sine 25, so we're not going to look at that again. And then we've got cos of negative 335. Okay, FG, we've got cos of negative 335. Do you remember what the rule is for a negative angle? We've written down the notes, consult them. Here it is. Here's the rule for a negative angle. It's exactly the same as its positive partner. So because the cos function is symmetrical about the y-axis, this will give me the same value as cos 335. And once I've reduced that to a terminal ray that I can now work with, I then reduce as I know from scratch. So I'm always trying to not construct, but to rewrite those angles into a mode that I'm going to be able to do that. Another way of looking at this angle is to say, if it's negative 335, I'm going to rotate in the opposite direction. So I'm rotating all the way there. So that's my negative 335. And then we talk about this angle over here being the coterminal angle. And the coterminal angle there is 25. So I could say that this is the same as the cos of 25, if you like. Or I can say it's 360 minus 25 to give me 335. So whichever way you like, you can find the coterminal angle, work with the coterminal angle. Some people find it easier. Others just say, you know what, let me use my cofunction rule, my negative rule, which means if I change the angle, I don't change the sign, stays the same sign, and then just reduce and say that that's 360 minus 25. Fourth quadrant, cos is positive, and there's the reduced value. So there are two different ways that will give you exactly the same answer. Over to you, Lumi.
All right, guys, we are going to take a very short break. I've seen all your questions here on Facebook, so I'll make sure that during the break I'll ask Dina as many questions as I can, and then when we get back she's going to go through the questions and answer them, or I'll just type them in as we go along. Guys, thank you so much for watching, and we'll be back straight after this break. Welcome back, guys. It's so good to see that you guys are actually asking questions where you're confused and you're focused and you're looking at what you're doing and what Dina's doing. So without wasting any more time, I'll take it straight back to Dina.
Thanks, grade 11s. You are really quite on the ball there, and it's exciting to see some of you helping each other. That's brilliant. There were two questions I want to go over. It's just a matter of clarity. and I'm going to go over them because they are very important. You are going to see this in your June examination, you're going to see it in your final paper, you're going to see it in your matric paper next year. That's how important it is. So I thought I would take just a minute to go back over those two very important concepts. One mindsetter asked, what happened to the negative that we got over here? Because that certainly is cos squared of 180 minus x. So what happened with the negative? Well, let's just go back to what it means. If we take the cos of 180 minus x, just the linear, it is the same thing as negative cos x. Why is that? Second quadrant, the cos in second quadrant will give me a negative ratio. So any linear function will have positives and negatives. Now look what happens. This little squared there should really be outside both brackets. It's really confusing to be in the middle there. But the moment I have written that as my negative cos x, I need to put brackets around the linear because I'm going to be squaring a linear. I'm going to be squaring a negative linear function. So the brackets have to be by the 2. It's not good enough to say that this function is going to be negative cos squared x, because that means something completely different. So if I have, for example, if I look at it in terms of numbers, I always do this with my children at school so that they can understand what we're talking about with the trig. If I have the number negative 2 squared and I have the number negative 2 all squared, does that mean the same thing? No. This is the additive inverse of 2 squared, which is negative 4, and this means square a negative number, which gives me 4. So the position of the bracket and the position of the power have got huge, immense impact on my outcome. And so it's the same thing with the squared. Okay? If the function is squared, it means that you're squaring a negative function over here. And if you're squaring a negative function, you are going to get a cos squared x, because I'm squaring it. A negative function times a negative function is a positive function. Whereas if I get this negative, they are two different things, and they are not the same thing, in the same way as these are not the same thing. So it's very important the way we write it. This is a writing technique for the trig function. This is a squared, and the moment we take a squared, you could have gone straight from there to there, and you could bypass that completely, because you know that a squared function, doesn't matter what it is, whether it's positive or negative, the outcome is still positive. So this is very, very important. And I would encourage you to go and work with the other negatives in the other quadrants and square them and see what you get. Because I can guarantee you the majority of you are going to want to be tempted into writing that. And the function's outcome is not negative. If you square a negative, you're going to get a positive. So if your coefficient is negative, there is a huge problem. You've changed the question. You're no longer dealing with the same function. So that's problem number one. Then the second one is, what happens with a 450? 450 is larger than 360. All you do, punch 450 into the calculator, take away 360 from it until you land up with an angle that is within your 90 to your 360. Then you're ready to reduce. So that's all. Anything bigger than 360, 720, 1080 degrees, whatever it is, take off 360s until you have an angle that is in that region, 90 to 360. So if I do this, I'm then getting, and by the way, mindsetters, one of you wrote that the 2 was over here as a coefficient. Be very careful. Where you place that 2 is going to have an impact on what you're saying. That's a squared. It's not a double. So just be careful with that. This means that I'm going to square a 90 minus x. And now that I have the sine of 90 minus x, Coco rule becomes cos x. I don't have to worry about the sign because the Coco rule only applies in quadrant 1, so the function will still be positive. So there's no sign change. The only sign change comes in second, third, and fourth if you're not using the STC ratios. If you're using the other 6 ratios, then you're going to get negatives. And if you square negative, it's going to be positive. Remember what I said? You can go straight there. Matric markers will give you the mark. But if you go straight there, you get naught. And you've actually now made it worse for yourself because the rest of the question is not going to simplify nicely, and you're going to get yourself into a very big jumble. Okay, so those were the questions that came out, really good ones for clarity's sake. Let's go on to identities, another problem area with grade 11s. Okay, the only thing about identities is you've got to be very good with your algebra. If you're not good with your algebra, you're going to struggle with your trig. Because whereas in grade 10, even grade 9, you worked with A's and B's and X's and Y's, you're now working with those very same terms, but they've just become trig terms. So instead of A, you're going to work with cos A. Instead of B, you're going to work with cos B. Instead of X, you're going to work with sin X, etc. So the whole algebra that you've learned, how do I add terms, how do I simplify, how do I divide, all those rules have to now be applied. So if you are poor in algebra, guess what? It's going to affect your trigonometry. Okay, so first one, A. We need to prove that this left is equal to the right. So the beauty about identities is they're giving you the answer. So you are getting an answer, and you need to work towards that answer. It's not like this empty vacuum where you don't know where you're going. They actually say, look, you need to get it to that. How are we going to get it there? Okay, we often work with a side that I can do something with. I can square, I can add fractions, I can simplify. So we work with that side. So there's a very technical way of doing this. You have to choose a side. So I'm going to choose my left-hand side. Okay, so the first question is to prove that sine x plus cos x squared is going to be equal to 1 plus 2 sine x cos x. Okay? And since I've chosen the left, you write LHS for left-hand side. And that is the same, or that's been given, not the same, it's been given as the square of that bracket. Now I'm not going to write the square. I'm going to say, what does it mean to square a bracket? It means I have two brackets that are being multiplied together, and they are the same. They look the same, they are the same. And how do I multiply them out? Well, I have a rule. You've all learned it. I FOIL it out, you often say. So let's FOIL it out. We get sine squared, and then we get the OI, the oil, the inners, and the outers. And can you see I get cos x sine x, and I get cos x sine x. So I get two of them. 2 cos x sine x. And then I do my lasts. So I get cos squared x. And then I look at it and I say, okay, on my right-hand side, I've got it. I've got that part. What about these two terms? What is sine squared x plus cos squared x? Square identity. It's equal to 1. So I can simplify and say, which is equal to 1 plus 2 sine x cos x. And then you say, which is the same thing as my right-hand side. So in other words, you have proved that if you write sine x plus cos x all squared, it is the same thing as saying that it's 1 plus 2 sine x cos x. So you have proved what we call an identity. Okay, let's just go back up there and see what the next one is. So take the left-hand side. Now, in B is a classic example of when you look at it and you say, well, I'm going to try and get all this into a tan x. Because it's a fraction, because there are terms in the numerator, because there are terms in the denominator, I'm going to simplify my left-hand side. So I would take my left-hand side, I would write it next door, I'd say left-hand side, and as I'm looking at it, I'm already analyzing it. I'm saying, well, what could I do with my numerator? What could I do with my denominator? Sometimes you can't do anything with the numerator, so you go to the denominator and you see, aha, I have two terms, and this cos x is in both terms. So do you remember factorizing the algebra? Being able to expand, being able to contract and bring things together again, being able to factorize, all those are tools for you to be able to do trigonometry. So in my left-hand side, I then sometimes start with what I can do, which is to take out the cos x, and then I'm left with the sine x plus 1. Now, this gives me a hint. If I have a sine x plus 1 in a bracket, then perhaps I would like my numerator to be in sine x. So my next question is, can I get the numerator into sine x? Is it possible? What is 1 minus cos squared x? And that's why now you have to be very well versed in the square identities. So I have to know that sine squared plus cos squared is 1, but you've got to know the ones that come through after that. 1 minus cos squared is sine. 1 minus sine squared is cos. Okay? And be careful that it's the squares. So it's got nothing to do with the linear. Sine x is not equal to 1 minus cos x, but sine squared is equal to 1 minus cos squared. So we now have that that's equal to sine squared x, and we've got this plus sine x. Oh, I'm sure some of you are jumping out of your seats at home to say, I can see, I can do something with my numerator. I have a common factor of sine x. So I can take out sine x, and what am I left with? A sine x plus 1 in my numerator over, no, we do not want to move that across, over sine x plus 1. Now I can divide, I can say that goes into that, and so I'm left with a sine x over a cos x. Remember our quotient identity? That tan is sine over cos, so we can now say that that's exactly the same thing as tan x. So, identities are about algebra. I have to be able to factorize. I've got to be able to add terms, I've got to be able to expand, and I've got to use the rules of algebra always to help me. Okay, see a classic example. I need to add two fractions together. Two fractions that contain terms in the denominator. I need to be able to be good at adding fractions in order to be able to solve this problem, which is not really a solving, but it's a proving of an identity. So we've got 1 plus sine, 1 minus sine. Let's take it down times the cos squared. Let's see if we remember that. So we've got, okay, so this was C. We had 1 over 1 plus sine x plus 1 over 1 minus sine x, and then we're multiplying it by cos squared x. Right. First rule about multiplying fractions is that we find our common denominator. So it's 1 plus sine x multiplied by 1 minus sine x. This fraction has got that. It does not have that second factor, so it's got to be multiplied top and bottom by that factor. That fraction's got that denominator. It's missing that, so it's plus 1 plus sine x. And then everything is being multiplied by cos squared x. So we now get that minus sine plus sine is 0, and 1 over 1 is 2, and we get this 1 plus sine x multiplied by 1 minus sine x. Okay, and we're going to multiply it by cos squared x. Now you have a choice. There are quite a lot of choices here. It doesn't matter which one you take. It's not going to make anything longer or shorter. I would say that you need to be able to recognize that sine squared x plus cos squared x is the sum of two squares. So it doesn't have any factors. But the derivation of the subsequent identities that come out of that, the 1 minus cos squared and the 1 minus sine squared, they're actually a difference of squares. So way back, I think it was in slide number 2, where we looked at the key concepts. Let's just go and look at that. No, slide 3, no, slide 4. Yeah, it was this one. Where we looked at these two here. This one's got no factors. But we now need to come and insert something here that's very important, and that is that sine squared theta is equal to the product of 1 minus cos theta multiplied by 1 plus cos theta. It is the factors of the difference of squares. And this one here, we've got that cos squared theta that's the difference of squares, so it's 1 minus sine theta multiplied by 1 plus cos theta plus sine theta. Okay, so two brackets, two linear brackets, if I multiply that, I'm actually getting 1 minus sine squared, but I can reduce that to cos squared, which is what we've just been working with. So you've got to be able to factorize both cases. So let's look at it. Okay. Okay, we'll leave it at that.
All right, guys, we are at the end of our show. So thank you so much for tuning in and joining us on our Facebook page and on Twitter. Though it's been very quiet on Twitter, I'd like to thank Macmillan for sponsoring our show and Dina for helping us out with the trig grade 11s. I've posted everything you need to know on Facebook, but you can go to our website on mindset. It's learnextra.co.za/live, where you get everything else that you'll need. Thank you so much for tuning in, guys. Until next week, same time, same place. It's goodbye from us.